Welcome back to the Transformer series. In the last video, we talked about why the old way of building translation model hit a wall. We saw the pain of recurrent network, the sequential bottleneck, and why the field was hungry for something better. Today, we are going to cover the single most important idea that came before the transformer, and the one most people skip. If you skip this chapter, the transformer is going to look like magic. It was not magic, it was the natural next step from what we are about to learn. Here's how I want you to think about the problem we are going to solve today. Imagine you just finished reading an entire chapter of a textbook. Now close the book. You get one sticky note and you have to write down everything you remember on it. Then, using only the sticky note, you have to write a detailed summary of the entire chapter. That sticky note is going to be pretty rough, right? You might capture the big ideas, but the details, the specific, the nuances, those are going to get lost. And that is exactly what an early translation model had to do. They compressed an entire input sentence into one single fixed size vector and then tried to generate the full translation from just that. Here's what we will cover today. First, why the old encoder decoder pipeline collapsed on long sentences. Second, how a technique called attention broke through that wall. Third, the actual math behind the attention explained so you can feel it intuitively, not just memorize the symbol. And fourth, why even attention was not enough and what gap the transformer was built to fill. If you skip this chapter, the transformer architecture is going to seem like it came out of nowhere. It did not. Every piece of the transformer built directly on what we are going to learn today. Before attention existed, neural machine translation followed a simple three-step recipe. Here's the picture. On the left, you have your source sentence, say French words like lit, chat, etc. etc. The encoder, which is an LSTM, read these words one at a time, left to right, updating its hidden state after each word. In the middle, you have that single fixed size vector. After the encoder finishes the last word, its final hidden state becomes the entire representation of the input sentence. That one vector is everything the decoder will ever know about the source. And on the right, the decoder, another LSTM, takes that vector and tries to generate the translation word by word. The cat is black in this particular case. So step 1, the encoder reads the source sentence token by token. Step 2, the final hidden state becomes one fixed vector. The entire sentence compressed into a single point in a mathematical space. Step 3, the decoder takes that one vector and generates the output. Here's the catch. Every thing, every word, every grammatical structure, every piece of the of meaning in the source sentence has to fit inside that one vector. For a sentence of 5 words, that might be okay. For a sentence of 40 words, that vector becomes brutal compression bottleneck. Let us actually see this bottleneck. On the screen right now, you can see a visualization. On the left, there are source words. In the middle, there is a fixed vector. Think of it like a funnel. On the right, the output words. Now watch what happens as I increase the sentence length. At word 3, funnel handled it fine, right? The capacity bar, this bar was green. The output also looks sharp, right? But as we increase the number of words, let's say 10, 15, 20 words, you can see the funnel getting overwhelmed. The capacity bar goes from green to orange to red. The output tokens on the right starts fading. They are getting blurrier because the decoder is working from compressed lossy representation. And this is the key point. The fixed vector act like a funnel. Short sentence flow through easily, but a long sentence gets squeezed and details are lost. The 2014 attention paper explicitly identified this as the bottleneck that needed fixing. So the question becomes, is there a way to avoid this compression entirely? What if the decoder did not have to rely on that one frozen vector? And that is the core insight. On the left, the old approach, right? The read whole sentence once, compress it into one vector, and then try to decode from memory alone, like closing the book and writing from one sticky note. On the right, the attention approach. At every single output step, let the decoder look back at the entire source sentence and pick out the part that matters most right now. Like keeping the book open, glancing back whenever you need it. This is the core of what is called as align and translate attention. Instead of a one frozen memory snapshot, the decoder gets a fresh custom built context vector at every output step. And that context vector is specifically focused on the most relevant part of the source for the particular word being generated right now. Not a general summary, a targeted word specific focus. Let us walk through the 4-step process that runs at every single decoder time step. Step 1. The decoder builds a memory bank. As the encoder LSTM reads every source word, it produces a hidden state for each word. Think of this as label memory slot. One slot per source word. And each slot captures the word in context, not in isolation, right? Step 2. At each output step, the decoder takes its current state and compare it against every single word, one of those encoder memory slot, right? It asks, for the word I am about to generate, how relevant is each source word? Step 3. Each source word get a relevance score. These raw score are then passed through something called a softmax, which turns them into proper weights that add up to 1. Essentially a probability distribution over the source word. Step 4. Multiply each encoder state by its attention weight and add them all together. The result is a single context vector, a custom blend, heavy on the relevant word, light on the irrelevant ones. Here's how I like to think about it. Imagine you are at a buffet. Okay, in the old system, someone hands you one pre-made plate. This is your fixed vector. You eat whatever is on it. With attention, you get to walk along the entire buffet line. This is all the encoder states. And take exactly the portion you need right now. And here is the key. You do this for every single bite. Every word the decoder generates, it builds a fresh custom plate from full buffet. Now let us ground the intuition with the actual equation. And I promise you we'll take them one piece at a time. First is the setup. The encoder has produced a hidden state for every source word. Call this source word as H1, H2 all the way to Hn for a sentence of n words. Each of those states is a rich vector, right? Each state, H1 as a state, is a vector. And it captures what the word means in the context of full sentence, right? Now the decoder is about to generate the next word. It has its own current state, which represent everything it has generated so far. And here is the first equation. In plain English, it says this. Take the decoder current state, that is st minus 1, and one source word representation, feed them into together into a small neural network. This A is, consider it as a neural network, and the network output a single score, right? This is called a relevance score. How relevant is this particular score, particular source word? How relevant is this particular source word? Okay, you're getting it, right? How relevant is this particular source word to what the decoder is trying to generate? Decoder generation is here, right? That is all this equation is doing. One number per source word, telling us how useful that word is at this moment. Think of it like a student translating a sentence. At each word, the student holds up their current draft and asks each source word, how useful are you to me right now? The small neural network is the judge that looks at both the draft, and the word, right, source word, and give a relevance score. And you might ask, why the neural network, right? Why do we need a neural network specifically? So earlier method tried simple dot products, just checking the surface similarity. But a learned network can capture much more complex patterns of relevance, things that are not obvious from just comparing two vectors directly. Now we have the relevance score for every source word, but these are just raw numbers, right? They could be any value. We need to turn them into proper weights. This is where softmax come into picture. Take the relevant score, right, and raise it exponentially. So every value becomes a positive value, right? Then divide it by the total. Now every weight is between 0 and 1. They all add up to 1, right? The most relevant word get a bigger share of attention. The irrelevant word get almost nothing. It's like converting the raw votes into percentage. And then the final step. Multiply each source word representation. Each source word, HI is the source word representation, by how much attention that we are getting from here, how much attention it deserves, and add them all up. The result is a single vector, CT. That is the context vector. That is the weight. That is a weight blend. It is a weighted blend. You can think about it. It is mostly made of relevant words only, with barely a trace of like some relevant words in there. This is called soft search, because instead of picking just one source word, which would be hard binary decision, we blend all of them with a different strength. And then everything here, the scoring, the softmax, the weighted sum, uses smooth differential operation. The entire system can be trained end to end with backpropagation. The model learns where to look as part of learning how to translate. Now let us see this whole mechanism work on a real example. On screen you have a French sentence here and then an English sentence just below that. It's a translation. We can click on any English word and see where the model focus, right? Where the attention is the most. Let's suppose I click European, you can see the attention is on this particular word. It's very difficult to pronounce French, so I'm not even going to try. You just have to look at my mouse pointer. The bar shifts completely right here. Then if I click, let's suppose zone, You can see this, right? The bar focused on zone. This is the attention. This is the score that it is getting. Let's say I go to growing on the last at the end of the source. The attention is 70% here. And notice something important here. The word order is different between French and English, right? It's more of a reverse order, right? But attention does not care about the word order. It learns the correct alignment regardless of how two language arrange their word. That is exactly why the original paper called this approach align and translate. So let us step back and see the full context, conceptual shift that is happening here. Before attention, the decoder got one compressed summary and had to work on the memory alone. Remember everything once, then decode. With attention, the decoder can look back at the full source sentence at every step, reopen the source at every step. It is difference. It is the difference between taking an exam with no notes versus taking an open book exam. The quality of your answer goes up dramatically. And this gave two huge wins. First, performance. No longer collapse on long sentences. The decoder can always reach back to any part of the source, no matter how long it is. Second, interpretability. Now you can visualize attention weights as alignment maps. You can literally see which source word the model focused on each target word. For the first time, you had a window into the model, what the model was thinking. After the initial breakthrough, the natural next step was, do we always need to look at every single source word? This is where the distinction between the global and the local attention came in. On the left, you have global attention. At every decoder step, the model attended all the source position. Every source word get a score. This is a most thorough approach, but it can be expensive for a very long sequence. On the right, we have local attention. The model first predict roughly where in the source to look, and then apply attend to a window around that position. Right? You can see here. Faster and sometimes sharper because it avoid diluting attention across words that are clearly irrelevant in the case of local attention. Think of global attention as wide angle floodlight that illuminate the entire room every time. Local attention is a focused spotlight that the model aim at the region it wants to sort of look at. So this is the region it is trying to look at in local attention, but in global it will look at the whole sequence. Okay. Both have their place, and the refinement work here led to substantial improvement in translation quality. So attention was massive leap forward, but there was still a fundamental constraint that attention alone could not fix. Both encoder and decoder were still recurrent. They were LST or GRUs. That means they had to process tokens one at a time in sequence. Token 5 could not be computed until token 4 was finished. Token 4 could not be computed until token 3 was finished, and so on. The sequential dependency made training painfully slow, especially on long sequence, because you could not fully use massive parallelism of modern GPUs. GPUs are designed to do thousands of operations at once, but recurrent model forced them to do one step, wait, do the next one, and then again wait. This is like having a 16-lane highway but only allowing one car through at a time. Even though the attention fixed the quality problem, the model could now handle long sentences well. The speed problem remained. Scaling to bigger data sets, longer sequences was still limited by its recurrent backbone. And this is exactly the gap the transformer paper targeted. And if you could get rid of recurrence entirely and keep only the attention mechanism as the core computation, no sequential dependency, full parallelism, attention handling all the contextual work, that is exactly what happened. That is what we will cover in the next video. Let me show you the sort of the lineage timeline that came in there. The timeline fills in as we go. So in 2014, sequence to sequence with a fixed vector, it worked for a shorter sentence but hit the wall of anything longer. That came into picture. In 2015, attention was added with dynamic context and learned alignment, and the bottleneck was solved, but the model was still recurrent and still sequential. In 2000 and then in 2017, the transformer came, remove recurrence entirely, attention as a sole mechanism, full parallelism. And you can see how clean the progression is. Each step solved the most painful limitation of the previous one. Sequence to sequence bottleneck was fixed by attention. Attention sequential training was fixed by removing recurrence. The transformer was not magic from nowhere. It was clean generalization of an already successful idea. Okay. Now, before we wrap up, there is an important caveat I want to leave you with, because once you start seeing attention weights, it is very tempting to overinterpret them. The exciting part was that once attention weights were available, you could visualize them on a heat map. For each target word, you could see which source word the model was focusing on. On the right, you can see a heat map of dark blue means more attention. Here dark blue means more attention. And these maps often looked remarkably sensible. Clean diagonal pattern for language with similar word order and interesting cross patterns for language with different structure. People got excited. It seemed like a window into model reasoning. But here is a caution. High attention weights on a source word means the model used that word representation when building its output. But it does not mean that the model's decision was caused by that word. Researchers have shown cases where attention weight can be rearranged without changing the model output, and the cases where mostly heavily attended words is not actually the most influential. So, the right way to think about attention map is as a helpful clues for understanding, not definitive proofs for reasoning. They are a starting point for investigation, not a final answer. Before we move on, let's make sure the core ideas have clicked. I'm going to put 4 questions on screen. Try to answer each one in your head before I reveal the answer. Pause and ponder. Question 1. Why is one fixed vector a bottleneck for a long sentence? Think about it. A single vector of fixed dimension has to represent the entire input. As sentences get longer and more complex, more information get cramped into same number of dimensions. Details blur together, nuances get lost, and the decoder ends up working from a lossy, compressed summary instead of the original rich content. Short sentence might fit, but anything beyond a few words start losing critical information. In plain language, what does the attention weight for source word I at a time step t represent? Think about it. Go back to that equation and think of it. It represents how relevant or important source word I is to the specific target word being generated at step T. A high weight means the source word matters a lot for what I am producing right now. A low weight means not very useful at this moment. And all weights sums up to 1, forming a probability distribution over the decoder over where the decoder is looking in the source. Why can attention help even before removing recurrence? Because attention and recurrence solve different problems. Recurrence is about how important how information flow through time. The bottleneck was about how information is compressed at encoder decoder boundary. Attention solved the compression problem by giving the decoder direct access to all encoder state at every step, regardless of whether those states were produced recurrently. So even in a recurrent framework, translation quality improves dramatically. What recurrence limitation remains in pre-transformer model with attention? The encoder and decoder still process tokens sequentially. Each hidden state depends on the previous one, so you cannot compute them in parallel. That sequential dependency is a throughput bottleneck. Modern GPUs can do thousands of operations at once, but recurrent models forces them to wait at each step. The transformer solves this by replacing recurrence with self-attention, where every position can attend to every other position in a single parallel computation. Okay, let us bring all this together. The bottleneck, fixed vector sequence to sequence compressed everything into one point, and that collapsed on long sentence. The solution was attention. Let the decoder look back at all source state at every step, building a custom context vector weighted by relevance. The variant, global attention looks at everything, local attention focus on a window. Both improve translation quality significantly. And the remaining gap, even with attention, recurrence force sequential processing. That is what transformer was built to eliminate. And this is exactly where we are heading next. In the next episode, we tackle the core transformer idea. No recurrence, no convolution, only attention block, feed forward layer and residual connection. You will see how encoder and decoder attention we just learned evolved into self-attentions everywhere, and why that single change unlocked everything from GPT to BERT to every large language model you interact with today. If that sounds like interesting, make sure you are subscribed so you do not miss it. I'll see you in the next one.